Okay, now we're finally ready to do some logic. As you may recall, I suggested earlier in the week that what we want to do in symbolic logic is use the language of FOL in order to help us say very clearly, under certain circumstances, that one claim follows as a matter of validity from some other claim or set of claims. So logic is all about necessity and possibility. Logic is all about determining circumstances where we can know that if some set of sentences is true, if we assume that they're true, that some other sentence will necessarily be true as well. And one of the things that is explored a bit in the book is this idea that there's more than one source of necessity. And one of the things that the book deals with, which we're not going to worry about, is this issue of one source that's relevant, just what we've done so far, is from the Boolean connectives themselves. That's what we're interested in. Another one can come from aspects of the world or particulars of the language that you're using to talk about the world. So what they call Tarski's world valid, Tarski's world necessity, Tarski's world possibility. We're not going to worry about that so much. That's not really our interest here. If you're trying to do more sort of philosophy of logic, that can actually be very relevant, trying to figure out these different sources of necessity. We're really only worrying about two different sources of necessity in this course. The one right now is from the Boolean connectives, and that's going to keep us busy through pretty much until next week as well. And then the last week of the course, we're going to look at these things called quantifiers, the words that mean things like all and some. In addition to the and or and not that we've been looking at so far. So how is it that the Boolean connectives themselves, the truth functional connectives, can generate necessity? Well, it comes from the way in which they are defined. They're defined such that given true statements or false statements as their inputs, they are going to have to give you certain sorts of true or false statements as their outputs. And if you put them together in certain sorts of combinations, you can end up in situations where something will be guaranteed to be true. And we're going to talk about three different ways in which that kind of necessity can manifest itself. Tautologies, logical equivalence, and logical consequence. So let's start with tautologies. So a tautology is any sentence whose truth table has only t's in the column under its main connective. So what does that mean? Why is that an interesting thing for some sense to have? Well, remember what this thing is. What is this left-hand business of a truth table all about? What the left-hand part of a truth table is for whatever's going on up here. It's taking all the basic claims in it, and it's listing out every single possible way that those claims could be true or false. Every single possible situation in terms of the basic claims themselves. But since it's listing all of the possible combinations, if it turns out that on every single one of those possible combinations the sentence comes out true, then the sentence is necessarily true, just based on the meanings of the things that go into the truth table, namely the ands and the ors and the nots. So a tautology is a sentence which is itself necessary, and whose necessity is produced by the meanings of the truth functional connectives, the Boolean connectives that make it up. So in this sentence here, it doesn't matter what A, B, and C are saying. You can put in some particular claims for those. There are particular claims about things in Tarski's world, particular claims about people, or particular claims about basic particles in the universe. It doesn't matter. Completely doesn't matter what A, B, and C are saying, because based on how not and or works, and the distance of these parentheses, there's no way for any statement that looks like this to come out as anything other than true. So one of the things I want to do is, in my lecture today, is walk you guys through bool a little bit and see how it works. So I thought I might do some of exercises 4.2 here on page 104. Before I get into that, though, one thing I want to draw your attention to, make sure you didn't look past too quickly, because it messed me up at first. When you're using bool, here's a very relevant thing. You can type things in directly, but don't use the caret symbol or the V for and or. You probably don't have this guy. You probably don't have a little negation symbol on your keyboard, so there's not much temptation to try to type that directly. Just use the tilde for that. If you try to type the caret, it will actually put up this weird upside down T symbol. Don't worry about that right now. But the thing that can really mess you up is if you type a V, it'll put a V up there, but it won't be the logical or symbol. It won't be disjunction. It'll just be a letter V. The thing you have to do to generate the or symbol, the disjunction symbol, is this vertical slash. Does it count as a slash? Anyway, the little vertical dude. It's on my particular keyboard. It's on the far right, just above the return key. If you hit shift in that key, you'll get that symbol. So let's go ahead and launch bool. Here's bool. We'll look at that in a minute. So I'm going to do 4.2 on page 104. So the first thing I'm going to do is put in the statement itself. So we're doing tautologies. We're just looking at individual statements. So I need an or, so I'm doing that little vertical guy. By the way, you should certainly feel free to go up and click on these things. So note here's I'm going to add an or by clicking on that symbol there. That's totally fine if you want to do that. I just find it a little cumbersome, especially when you've got a lot of symbols going up before you type. So there's the statement we're going to be interested in. Now we have to generate the reference columns. So first we have to see what are all the basic statements that are made here. Well, just A and B. So that's pretty easy. There's B. And column 4, A. But we'll suggest that you work from right to left, and I think that does make sense to me when you're just constructing the reference columns. So now, our job here is to list out all the possible situations in which all the combination of ways that A could be true or false and B could be true or false. And when there's just two, it's pretty straightforward. There's a total of 4 lines. And I do 2 trues and 2 falses, and then true, false, true, false. One thing you'll find with these truth tables is that the rightmost line is always going to be just true, false, true, false, true, false all the way down. And so you know this is all the possible ways that A and B could be true or false. They could both be true, they could both be false, A true, B false, A false, B true. So now what we want to do is determine, is this whole statement true or false on each line? Now, bool is nice enough to highlight the main connective here. This is the outermost connective. The main thing the sentence is an or. It's an or linking these two subsentences. So before we can determine whether that or part is true or false, we have to determine whether the subsentences, the things that are inputs to it, are true or false. So to do those, we click on that column, and notice how these things have popped out in green. What it's telling me is determine what goes on in this little turquoise box. These are the inputs that I need. So on this line, so the sentence is A and B, and this is the line where A is true and B is true. So on this line, on this row, A and B is true. On the second row, however, this represents the possibility where A is true and B is false. Now, in that kind of world, in that situation where A is true and B is false, then A and B is itself false. Here's a situation on the third line where A is false and B is true. In that kind of situation, A and B is going to be false because they both have to be true in order for A and B to be true. Now, negations are super easy to do. All you need to do is just take whatever the input column is and flip it around. So this is not A, so A was true, true, false, false, so the not gets false, false, true, true. And here, this is not B, so where B is true, not B is false. Where B is false, not B is true. And now we're ready to do this OR. So this is an OR, so either one or the other one is all that it takes. But this first line, neither of them is true, so it's false. So note in particular, wait, see how when I'm doing this column, the things that are popping in green are over here, not over here? Because what's this OR connecting? It's connecting not A and not B. We don't want to look at A or B by themselves, we want to look at the nots, the not A and the not B. So that's what's lighting up over here. And this line's true because remember, it's an inclusive OR. So now we're ready to go to the main connective. It's an OR, so we need one of the other to be true, 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 true. So, is this a tautology? What we're asking by asking is this a tautology is every single line in the truth table one where the whole sentence is true. So we look, here they are. Those 4 lines, it's true on all those lines. So I go to assessment, I say sentence is a tautology, I click OK. Now, all I've done so far is I've told Google what I think, but what's great is that Google can tell me if I got it right or not. We're going to verify, and we got it right. Excellent. So let's do another one. So then this is 4.2 on page 104. Let's go ahead and do number 4 on 4.2. So you can see what it's like when you have an A, B, and a C. Oh, okay. I almost forgot to put that last parenthesis in there. So there's our statement. So now we have an A, a B, and a C. So we have 3 basic statements, and so we're going to need 3 columns. And now there's going to be twice as many rows as before. Every basic statement you add doubles the number of rows that you're going to have to worry about, doubles the number of situations that are possible combinations of trues and falses. So when there's just 2, there are 4. When there's 3, there's 8. So the way to do it when there's 8 is for the first one to do 4 down, maybe 4 trues and 4 falses, then do them in pairs. And then the rightmost one is always just true, false, true, false, true, false, true, false. Okay. So we want to do this guy, but before we do that, we have to do these 2 guys here. So let's do this one. That's going to be pretty straightforward. So in this row, this is a situation where A and B are both true. So A or B is true. True. If one's true and the other one's false, the OR is true. Once the other one's false, the OR is true. A is false and B is true, so A or B is true. It's just these last 2 where A and B are both false. These are situations where this guy is going to be false. So the only situations where this guy is false is where A and B are themselves both false. So to do this, we have to do this one first. And to do that, we need to do this one first. So we've got B and C. So we need to see that they're both true over here. True, false, 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 true, false, false, false. Right, so this line is one where they're both true, but for example, this line, one's true and the other one's false, so the and is false. So for the OR, so notice what's going on here. It's lit up this green thing over here and this green thing over here. This OR is connecting 2 things. It's connecting A by itself to B and C. So we want to know is A true or is B and C true? This is representing when A is true. This line is representing when B and C is true. So that's why we're going to look at those 2 things. So on this line, A is true and B and C is true. So the whole thing is definitely true. On this line, A is true and B and C is false. So the OR is true because it just needs one or the other because it's an OR. Similarly here, similarly here. Now on this line, look here on this line, it's the 5th line. The A is false, so this left disjunct is false. But the right disjunct, B and C, is true. So the whole thing is true. But now, all the rest of the ones, it's going to be false. On these last 3, note that both of the inputs are false to it. Okay, now let's look at the next thing we need to do. Are we ready to do the main connective yet? Oh, no. We still have to do this negation. So what's this negation doing? It's taking this whole thing, which is represented by this column, and it's saying that it's false. So note when I click in here, it's highlighting this area because it's negating this whole thing. So again, negation is always really easy. Just take whatever's in green and flip it around. All right. So now I think we're ready for the main connective. And so it's an OR, so we see one of the other one to be true. And it looks like true is all the way down. So we look at that main connective, we see that it is true on every single line. I'm sorry, I need to get the assessment first. It is a tautology. And we did it right. So by the way, what happens? Suppose we did it wrong. So somewhere along the way, we messed up and put a false in here. All right, so that's a mistake. This is true or false, so that should be a true. But suppose we weren't paying close attention, we put a false there. And then we look here and say, wait, there's a situation where the thing could be false, so we say it's not a tautology. Then we ask it to verify, and it's going to tell us not just that we were wrong, but it's going to tell us where we're wrong. We got this line messed up. So now I want to talk about logical equivalence. So for tautology, we look at an individual sentence, and we want to see if its truth table is true all the way down. With logical equivalence, you're not trying to see if anything's true all the way down. So here's one on page 106, where it's looking at one of De Morgan's laws. And remember, so this is equivalent to this, not A and B. It's not the case that both A and B is true. It's the same as saying, well, either A is false or B is false. Now, note that neither of those statements is itself a tautology. Right? Here's a line where that's false. Here's a line where that one's false. So neither is a tautology. Our interest in logical equivalence is not to say that of 2 sentences that they're both always true. Rather, what we want to say is that whenever one of them is true, the other one is true. Whenever one of them is false, the other one's false. That they stand and fall together. That's our interest in logical equivalence. But it's the same basic idea of you fill out the truth table. You want to look at for every single possible situation, which is true and which is false. And then you want to see that they all line up. So one important difference here between tautology and equivalence is that you're going to be doing two statements with equivalence and not one by itself. And the other major difference is instead of looking to see if it's just true all the way down, what you want to see is where there's false for one, is there false for the other, and when there's true for one, is there true for another. So note again that this satisfies that definition. Wherever this one is false or true, this one is false or true. So let me work through an example of that for you guys as well. So I'm going to claim that the following things are logically equivalent. So I finished typing one statement. Now you don't just want to keep typing. When you're doing more than one statement, you have to add another column. So I'm going to add a column after. It gives me a little separation thing. It's numbered them differently. Okay, they're both green, so I'm good to go. So I'm claiming that these two things are logically equivalent. Now I've got just two basic claims here, A and B, so it'll be a fairly straightforward table to fill out. Whenever you just have two statements, the reference columns are always going to look like that. Okay. So now since there's two statements here, notice there's two gray horizontals, one for the main connector of each. And what I want to find out ultimately is this column and this column should just look the exact same as each other. But it's going to take a little bit of work to get there. So I click here. This is A and B. So on this row, A is true and B is true. So together they are true. On this row, the second row, A is true and B is false. So the and is false, false, false. Now I can't do this one quite yet. I can't do this other and because I need to do this negation first. But again, it's always really easy. It's just a matter of flipping the truth values around. If B is true, false, not B is false, true, false, true. Now we're ready to do the and. So here on this line, you have a true and a false, so it's false. On this line, true and a true, so it's true. False and a false, so false. False and a true, so false. Now we're ready to do this column. So it's taking input from here and from here. Right? This or is linking this sentence and this sentence. This column represents when this sentence is true, and this column represents when this sentence is true. So I want to see what's in those two columns, and it's an or. So I just need one to the other side to be true. So on this line, one to the other side is true, so it's true, true, false, false. Okay. So I want to do, so I've got this one filled out, now I want to do this one. So to do this negation, first I have to do this other negation. So this negation is negating this thing. So this is pretty straightforward. Just take the A and flip it. And then this takes this one and flips it. Note, by the way, what you can see here, when you see that this is true, true, false, false, and this is true, true, false, false, is the logical equivalence of not A and A. It should be unsurprising that this column just looks the same as that column, because we already learned earlier in the course that A and not A are logically equivalent. Okay, so now we filled out the truth table for both of the statements. So you note that neither of these is a tautology. That's not the question we're interested in right now. Our question is, are they logically equivalent? So for each line, are they either both true or both false? And you can see that they are, because here it's true, true, false, false, and here it's true, true, false, false. And so assessment, the sentences are tautologically equivalent, and I'm going to ask it to verify. And we got that right. So the difference between doing tautology and tautological equivalence is tautologies, if you're trying to cite a sentence by itself, is necessarily true. With tautological equivalence, you want to know, as a matter of necessity, do the two sentences stand and fall together? So the last kind of thing we're going to talk about now is logical equivalence. It's just more of the same. You fill out the truth table, you look at the statements, and you see how they're related. But tautological consequence is the one that really maps directly into our notion of validity. So remember, validity says, suppose you've got some set of claims, and you assume they're all true. Does the conclusion have to be true as well? And what that translates into in truth table terms is you fill out the truth table for all the premises and the conclusion. And they say, what lines of the truth table are ones where all the premises are true? Because if I'm assuming that all the premises are true, I can ignore any line of the truth table where any of my premises come out false. All I care about is situations where all the premises are true. I look at those situations, and I look over at the conclusion, and I see, is every single one of those lines a line where the conclusion is true as well? So however many lines are the ones where all the premises are true, are those same lines ones where the conclusion is true? Now it's okay if there are also some lines where some of the premises are false and the conclusion is true. That's totally fine. We're just looking at consequence here, not equivalence. So with equivalence, we want to know, was it always true on one side and false, true together or false together with equivalence? We don't really care about false together with logical consequence. All we care about is when all the premises are true, is the conclusion also true? So let me do one of those for you guys. So what I'm going to do is actually kind of simplified version of 4.22 on page 113. I'm not going to bother using the Tarski talk stuff. I'm just going to turn it into some A, B, and C. So that's a lot easier. So we're just going to use A by itself for one of the premises, B or C for another premise. And the claim is that either A and B is true, or A is true and C is true. So my claim is that this is a logical consequence of those. So we've got an A, a B, and a C. So it's going to be a longer truth table. And we'll do that. Okay. So there's going to be a total of 8 lines. So we can have 3 basic claims. We have a total of 8 lines. Start with a 4 and a 4. 2, 2, 2, 2. And then the rightmost column is always just true, false, true, false, true, false, true, false. So if there's 3 basic claims, there's 8 different ways the world can be, depending on which particular combinations of true and false there are. So this column is going to be super duper easy. We just copy the A column down again. Super trivial. B or C, well, again, it's going to be pretty easy. We just look here. When B and C are both true, that's true. true, true. That's going to be false. True, 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 and that's going to be false. Okay. So this one's going to take a little bit of doing. No, by the way, link this one up as well, just because it knows it's just the same as that. Don't let that throw you off. So here we got A and B together. So true, true, false, 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 false. Right. So on these first two lines, A and B are both true. On these two lines, B is false, and on these four lines, A is false. So these are the only two lines where that's going to be true. Now what about this one? When are A and C both true? Well, they're both true there. C is false there. Both true there. But C is false there, and then A is false everywhere else. Okay. So now what we want to know, we finished the filling out the, we have finished the table. What are we doing? We haven't done the main connected yet. So now we need both of these inputs. So that's an OR, so just one or the other has to be good. So true, 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 and it's false everywhere else. Okay. So what we want to know now is every single line where all of the premises are true is the conclusion true as well. So that's this line here. So remember, you can still look at those gray horizontal, those gray vertical bars. They're there to help you. So this line, both premises are true. Is the conclusion true? Yes. On this line, both premises are true. Is the conclusion true? Yes. This line, both premises are true. Is the conclusion true? Yes. So far so good. This line, one of the premises is false, so it doesn't matter. We're looking for a logical consequence. We only care about situations where all of the premises are true. And then these last four lines, note that one of the premises is false, so they don't matter either. All we care about are the lines where all the premises are true. So just these three lines, in this case, out of these top three lines, are ones where both premises are true, and the conclusion was also true there. So it turns out that this sentence is a logical consequence of those other two. So I'm going to claim that the last sentence is a tautological consequence of the others. And we ask us to verify, and we are right. Now, the ones that you're asked to do, the exercises are kind of longer. Part of the point of this exercise is just, as in general with exercises, often you do them harder than you need to do them because that's how you have to do things to get better. Also, there's a further educational purpose with having to do these long and tedious truth tables, as they say on page 113. It's good for the soul to build a large truth table every once in a while. But part of what we're setting up is the reason why you really want to do proofs. You don't want to have to do everything in terms of truth tables, because as soon as things get even moderately complicated, truth tables get huge and very boring. And so proofs are a much better way to do it. So part of the way of seeing that is if you make yourself do 4.23 and 4.24, as I've asked you to do, you will see that it's not something you want to have to do on a regular basis when you're trying to evaluate validity. So let me go ahead and set up. I'm sure you how to set up the reference columns for these, just because they're somewhat longer. So if you look at 4.23 of A, B, C, and D. Okay. So when we have two basic claims, we have 4 lines. When we have 3 basic claims, we have 8 lines. When there's 4 basic claims, we have 16 lines. And by the way, look at 4.24. You have A, B, C, D, and E. It's going to be 32 lines. Let's just do the 16 first. So for the leftmost one, you want to do it half and half. So I have 16 total lines, so 8 and 8. Let's stretch that out a little bit. Okay. So now if we did 8 and 8, we want this one to be 4 and 4. And 2s. And then just true, false, true, false. Okay. So that is how you'll set up the reference zone for 4.23. Here is what 4.24 will look like totally set up. It is a monster. I couldn't even get it all on the view. You have to scroll up and down for it. So it's 32 lines long. 32 lines long. 16 trues and then 16 falses for A. 8 trues, 8 falses, 8 trues, 8 falses for B. 4 is for C. 4 true, 4 false, 4 true, 4 false, 4 true, 4 false, 4 true, 4 false for C. 2s and then 1s again. And then I went and typed these out just so you can see, this looks like we have 4 statements going. Again, it's the same basic idea though, is one of these is the conclusion, everything else are premises. And what you want to know is for every line where all the premises are true, also a line where the conclusion is true. Any line where any of the premises is false, you just disregard. All you care about are lines where all of the premises are true. So, good luck and have fun. So, I don't have a whole lot to say really about section 4.5 in the book. I think it's fairly straightforward. I just thought that maybe the thing I could do would be to work through a couple examples. So I've worked out a couple. So first of all, here's one I've just made up. Let's keep here is a sentence, and we're just going to show how we can use equivalences to simplify it. One of the things that we're doing here, by doing the simplification stuff, is we're practicing a little bit of the kind of thinking that's involved in doing proofs, where you take one sentence and you apply rules to it to generate other sentences. One thing that's really cool about equivalences is you can actually apply it to the interior parts of sentences. We're not going to be able to do it with every single rule we're going to use, as you'll see next week. So one thing to notice here, just think about what's being said. So this is saying that 2 things are true. This and all this. What's this say? This says it's not the case that both A and B are, it's not the case that either A or B is true. So that's the same as saying that A is false and B is false. But this is just saying that A is false. So it seems like maybe we should have some way of getting rid of that redundancy. This is a little bit redundant with this. If this thing is true, this has already got to be true. And it turns out that just based on the rules that we have so far, these equivalences that we've got, we can actually show that we don't need both this part and all of this. So first I'm going to apply De Morgan's law. So I've taken this and transformed it into that. So the negation goes to the inside and the or flips to an and. So now I've got nothing but ands, and I got a not A over here, not A over here. So I should be able to, if I can get both of the not A's next to each other, I can use the idempotence law to get rid of it. Now how can I do that? Well, first of all, I can just flip these around, right? The commutativity of and says if I've got this and this, then I can just put them in the opposite order. And now the associativity law lets me take these parentheses and just scooch them on over. So you see the only difference between this line and this line is I moved over the parentheses. Again, we can do that because they're all ands. We could also have done it if it was all ors. What you cannot do is use this rule if you have a mix of ands and ors. But since it's all ands, we can use the associativity principle there. Now this is just redundant. This is saying not A and not A. And so the funnily named idempotence rule lets us get rid of that. So this whole thing turns out to be equivalent to just this simple little guy here. So that's what I made up. Now, let me actually do an example from the exercises. This is the one exercise I did not assign. This is 4.37 on page 122. Now, it took me a minute looking at it to realize what the redundancy is in here. It's that you have this, or this, or this, or this. And the thing that's redundant is this part here and this part here. They're saying the same thing, that both A and B conjoined. So what we want to do is get them lined up next to each other and make them look exactly the same. Once we do that, we can use an idempotence rule to drop out one or the other of them. So the first thing I want to do is take this and I can't speak. Switch it around so that we get this thing next to that thing. So the rule that lets us do that is the commutativity of or. So I took this and I just switched it around to be that. Because you can do that when you have an or, you can just rearrange the order of the two things inside the or. So one of the things to notice that we're doing here, this is one thing that starts to give some people trouble, people who had no trouble with this sort of material until this point, is that all these rules apply to whole sentences. It doesn't have to be just individual letters. So if you look at the rule of commutativity, you might think, wait, it just talks about individual letters. How did I move this whole thing over to the other side of the or? But the or doesn't really care how complicated the two things are. It just doesn't matter. All the or cares about is that this is giving it some sort of truth value, and this is sending it some sort of truth value, and if one or the other of them is true, then the whole thing's going to be true. So you can apply these rules to complicated, logically complicated sorts of things, and indeed we're going to see that again in a minute. So what's the next thing we can do? So I've got this next to this, but they don't quite look the same. I need them to look exactly the same. So all I need to do is swap this guy around. By the commutativity this time, and. So commutativity or lets us swap things around, and or commutativity and lets us swap things around, and. So this is just a textbook example here. We're just taking these atomic letters and swapping them. So now I'm almost done. I've got this redundant thing here. A and B or A and B. So I've got the same thing twice around an or. And so the idempotence rule lets me just drop one of them out. I just don't need them both. So that's as far as this one can be reduced. And so we're done.